I hope I am audible. I think there are some new members in the class, so I will recapitulate the things that I have done in the previous class itself. So I hope my screen is visible and also I am also audible. So I think one of them can confirm me. Hello.
Yes, sir.
Oh, I will look into your problem later on, Vasundhara, and then I will get back to you. Even I have
Okay,
any issue regarding the problem itself, I will like it's given there that no, it is given to be. I think it is given to be wrong. I can see it. It is wrong. It should be minus k dtdx plus hl t.
okay, sir.
Otherwise, let me do it. T infinity is something. Second, t infinity minus t. So, no, no, let me. So t infinity is between t and this t naught and tl. Is it given like that?
Yes, sir.
Oh, that's why the sign actually changes. Hmm. Okay, I will give it to you. That's why the sign changes. I will look into it. Okay.
Okay, sir. Okay, thank you.
Okay. So what we did in the previous class was that we started with something which is called discretization. So I will kind of recapitulate the things that I've done in the previous class itself. So give me a few minutes to get ready with the thing that I'm going. Okay. So as we have discussed earlier, that if I go to the format of the general transport equation, so we can see it here that it is basically equal to this ddt of rho phi plus del dot rho v phi equals to uh, del dot gamma grad phi plus s. So s is basically the source term and phi is basically your let me see what it is going to be. So phi is basically the scalar quantity. So it can be a scalar, it can be a vector also. So for our case, we are considering phi to be equal to T, where T is a temperature. So the first term is basically the temporal term. The second term is a convective term. The third one is basically your diffusive term. And the last thing, or S, is basically your source term. Okay. So this gamma, capital gamma, is basically your diffusivity coefficient, and which is basically in your case that will be equal to that of the thermal conductivity, or you can, yeah, conductivity. And rho is basically the density. Okay. So for example, if phi is basically equal to that of the velocity itself, so If it is velocity, then it becomes ddt of rho v plus del dot rho vv equal to del dot gamma, or then gamma is basically what? Mu. So mu del v plus s. So s is basically what? Minus of grad p plus rho g. Okay, the source term in your equation. So if I put the source term in the equation, that is basically ddt of rho v plus del dot rho vv equal to del dot grad of v minus of grad of p plus rho g. So now this reduces to a Navier-Stokes equation. Okay, so this you should be so general transport equation is pretty much the general form of any transport equation you have in your transport phenomena problem. So if I actually put this phi to be equal to that of the velocity vector, and then I put this gamma equals to the viscosity of the fluid, dynamic viscosity of the fluid, and S is basically the source term, which is equal to minus of grad P plus rho G. So this actually becomes a Navier-Stokes equation. So when we are actually solving a fluid problem, what you have to do is basically you have to solve the continuity equation with that of the Navier-Stokes equation. Okay, so you have to solve them in a coupled manner. So there are multiple methods of doing it. That can be by using projection method, that can be by using simple algorithm, but those are pretty much complex method which I'm going to cover in the later on classes. So what I'm going to do as of now is basically I'm considering this phi to be equal to that of the temperature, which is a scalar field, and then what I'm going to do is basically put the temperature right here, and then what I'm going to get is basically the heat conduction equation. So what we discussed previously was that there are different ways of dealing with this equation. So what we are going to do, since this one is a CFD course, we are going to discretize this equation. So for the uh, sake of simplicity, we are taking it to be like grad of phi plus a is equal to 0. So this one is basically called the diffusion plus source problem. Similarly, you can consider other terms also, and then you can convert that into a convection diffusion source problem or unsteady convection diffusion source problem. So there are multiple problems like that. If I write it like this, and this one becomes convection plus diffusion plus source problem. Similarly, if I write it to be like unsteady one, so this becomes ddt of rho phi plus del dot rho v phi equal to del dot gamma grad phi plus s. This is basically unsteady convection diffusion source problem. Diffusion plus source top. Okay. So initially, what we are going to do is you can consider it to be like tail dot gamma grad phi plus s, which is basically your convection source problem, and then you can solve it. And first, we will discretize by using the central difference formula, and we are taking a simple problem for the sake of simplicity. And then what we are going to do is basically we are going to solve it by using this. Let me share the screen. Then what we are going to do is basically we are going to solve this by using convection diffusion, by using central difference method. Difference. Okay. So is it clear up till now?
Yes, sir.
Others in the class? Arpan, Pawan?
Yes, sir.
Okay.
Yes, sir.
Hmm. And so how to solve the problem? So before solving any kind of CFT problem, what we do is that we discretize the whole domain into small control volumes. Okay. So as I have said earlier, there is a certain nomenclature we follow while dividing the whole domain into control volume. So for example, consider this to be a 1D rod through which heat is flowing. So there are two ends, one is A, another one is B. And then what we are going to do is basically we are going to divide the whole domain into multiple parts. So for example, 1, 2, 3, 4, 5, and this one, this one, this one, this one, this one, and this one. 4, 5, 6. For example, there are six control volumes which are present in my domain. Okay. So for example, my control volume of interest as of now is basically my third control volume, which is my control volume P. Okay. So what I'm going to do is that I'm going to put that point P here. Okay. So this is my control volume of my interest, and capital E is basically my east control volume, the control volume which is present at the eastern part of my control volume of my interest. So I'm going to write the equation for this P control volume by the way. Okay. And this one is basically my west control volume. And small w is basically, and small e, they are basically the points where which we are basically finding the common surface between capital P and capital W and capital P and capital E. Okay. So this is the nomenclature we are going to follow. Is it clear to all of you?
Sir, this is finite volume, right?
Yeah, this is finite volume. So what we are doing is basically we are solving the equation in the cell center. So if it is finite element, then we will solve the equation at the nodes. So we should have solved the equation at small w and small e itself. So here I am discussing only the finite volume itself. Okay. So then what I'm doing is basically tail dot gamma grad phi dv plus s dv is basically equal to 0. So my control volume P is having this equation. Okay. So since I've said earlier that this is my convection source problem, so sorry, diffusion source problem, and therefore I'm considering only two terms in the general transport equation. And then what I'm doing is basically I'm integrating with respect to that of the differential control volume. And then what I'm going to do is basically I'm going to discretize it. Okay. So how I'm going to discretize it? So this actually becomes, I have to convert this volume integral into a surface integral. So that I do by using Gauss divergence theorem. So in cap dot gamma grad phi plus s dv equal to 0. Okay. So now your n cap actually becomes what? This is basically equals to I cap, and this actually becomes, it is I cap dot gamma I cap d phi dx at east minus of I cap dot gamma I cap d phi dx at west and capital A, and then plus s dv equal to. Is it clear to all of you? Hello, am I audible?
Yes, sir.
Okay. Is it clear to all of you that how I'm basically doing it? Then I dot I will basically give you a unit that is 1 and gamma d phi dx a at small e minus of gamma d phi dx a at small w plus of is dv control volume at p equal to 0. Okay. So what I have to do now is basically I have to convert these into an algebraic equation itself. So what I'm going to do is basically I'm going to uh, uh, basically use finite difference in order to find out the finite volume with the Taylor series expansion in order to find out the value of this derivative. Okay, so how to find out the value of this derivative? So phi j plus 1 is basically equal to phi j plus d phi dx j delta x. So I've extensively covered in the previous class itself to how to do it. Uh, I will also upload the video so you don't have to think about it. So this square by 2 factorial and dot dot dot, which are basically these are the truncation errors. So I'm basically not running, writing these higher order terms in order to reduce numerical complexity. Okay, so then phi j plus 1 minus of phi j divided by delta x. Now the derivative at, sorry, d phi dx j is basically equal to phi j plus 1 minus phi j divided by delta x minus of del square phi dx square j delta x by 2 factorial. Okay, so that's how you find out the derivative. Okay, so basically this is first order accurate. So this is called forward difference method, by the way, forward difference. So one of the thing is basically what you are doing seeing is that this is actually first order accurate. So we are basically trying to use a second order accurate scheme, which is a the central difference method. So why it is first order accurate? Because this one is the order of delta x. So as I've said earlier, the exponent of delta x actually shows you the order itself. So if it's a function of delta x square, so then it will become second order accurate. Okay. So that thing you have to do. So how to do it? Similarly, we can write phi j minus 1 equal to phi j minus of d phi dx j delta x plus of del square phi del x square j delta x square by 2 factorial. Okay. Then we can write d phi dx j equals to phi j minus phi j minus 1 divided by delta x plus of your truncation error or leading term error. What you the first term is basically called the leading term error that I've said earlier, delta x by 2 factorial. This is total. The higher order terms is basically called the truncation errors. Truncation errors, and the first term is basically called the LTE or leading term error. Leading term error. Is it clear to all of you? So this is called the backward difference method. Okay. So then what we are going to do is basically find out the central difference formula also. So for central difference, you can find out by the methods of undetermined coefficients that I've discussed in the previous class itself. Where what I did was actually I multiplied the Taylor series expansion with A, B, and C, and then kind of solve the linear equation in order to find out the value of the constants. So from there, you can basically find out that d phi dxj equal to phi j plus 1 minus j plus 1 minus phi j minus 1 2 delta x minus of dq phi dx cube delta x squared divided by 3 factorial. Okay, so is it clear to all of you? This one is a central difference method. Okay, is it clear to all of you?
Yes, sir.
Okay, so another thing I will also show you, which I think I should show it. As of now, I don't want it. So, so one thing you can do is basically what you will do is that you are going to solve that equation by using central difference method and discretize the equation that I have shown earlier. For example, this equation itself. And then what we are going to do is basically create a set of linear algebraic equation and solve them by using matrix. Solve them by using matrix. Okay. So today I will show you how it actually this linear set of these equations actually give rise to a matrix. So then what you have to do is basically this is point P, this is point T, this is point W, and this is small w and this is small e. So which is basically the cell phase between common cell phase between the east cell centroid and the P cell centroid, and small w is basically the cell phase between that of the west cell centroid, which is on the left hand side of the P cell centroid and the P cell centroid itself. Okay, so this is basically the interface between the control volumes, the P and the E control volumes, or the small e itself, and small w is basically the interface between the capital P and capital W control volume. Okay, this you should keep in mind. So as that I've written earlier, so gamma A d phi dx E minus of gamma W A W d phi dx small w plus this thing is bar delta V equal to 0. So now it becomes gamma E A E. So basically A is basically your dy into dz, dA basically dy into dz, which is your differential area. So that thing itself is, by the way, constant in your case itself. So you can consider this as capital A only or capital gamma only. But as of now, I'm writing it to be a more generalized version. But these are basically constant. When I'm giving a problem, that will be constant over the whole domain. So that will not be a spatially varying area or spatially varying diffusivity. So if it's a spatially varying area or spatially varying diffusivity, then this small subscript E and small subscript W actually comes to be a handy one. That complexity we are not discussing as of now. So this actually becomes phi E minus phi P divided by delta X, the distance between them. Phi W A W is basically equal to phi P minus phi W divided by delta X WP. For this delta X, I can write it to be delta X EE plus of A bar delta V equal to 0. So now this equation becomes gamma EAE divided by delta HPE, okay, phi E minus of, or you can also uh, write it like this directly. So phi P is basically equal to phi P gamma W AW plus delta X WP plus gamma E AE delta X PP or PE, sorry, PE equal to gamma W AW plus delta X WP YW plus gamma E AE delta X PE I. Okay, and then there is a source term. So that will basically come here on the right hand side of the equation. So this will be equal to that of or mm, yeah is delta V. Okay, so is it clear to all of you that how I have displayed as an equation by using central difference formula?
Yes, that's pretty clear.
Yes, sir.
So then what I'm going to do is basically uh, so this is delta V which is present there. This can be written as uh, ACU plus SPTP. Don't ask me as of now that why I'm writing it like this. Generally, we write it like this. So ACU is basically your constant. So if it's a constant source term, only the ACU will be there. SP will be equal to that of 0. So what we do is that, first of all, what we are doing is that we are linearizing the equation. So even if we get it like TP squared itself, I will consider it to be like TP star and TP. So TP star is from the previous time step and TP is also of your the current time step for which you are solving the equation itself. So for simplicity, we are considering it to be like AC plus SPTP. Okay. So you can come and ask me that why I'm not considering it to be like AC minus SPTP. Okay. So that can be done, but if it's of the format of AC plus SPTP, SP should be negative. So this is according to the Scarborough criteria, which actually gives you the diagonal dominance in a matrix. So which I will discuss later on. So SP should be negative if you want it to be a convergent solution. Okay. So ACU is basically, as of now, if I considered it to be like a constant source, then ACU is not equal to 0 and SP equal to 0. Okay. If A squared V bar is constant. It's not a linear function of comparison. That can be a quadratic one also itself, but by using Taylor series expansion, we will consider that convert that quadratic variation into a linear variation. That can be done. So our main aim is to basically convert the partial differential equation into a linear algebraic equation, into a set of linear algebraic equations. So is it clear to all of you? Hello, am I audible?
Yeah, you're audible.
Yes, sir.
Okay.
Yes, yes.
So if I write it this S as AC plus SPTP, so my equation I am writing it to be a more generalized form, which is your is phi p gamma E A E by delta X P E plus gamma W A W by delta X W P and minus of SP equal to gamma W A W by delta X W P phi W gamma E A E like delta X P E phi E plus PC. Okay, so is it clear to all of you?
Yes, sir.
Okay, so as you've seen here, what I've done is basically I've only dealt with the cell centroids which were the interior ones. For example, these 2 to 5 are basically your interior cell centroids. Okay, 2 to 5. So this is the equation for 2 to 5 cell centroids. Okay. So there are boundary cell centroids, boundary control volumes also, or you can write it look like 2 to 5 control volumes. So there are some boundary control volumes also. For example, this 6 and 1. So why we should treat it in a different manner, that I will explain. So as I have said earlier, one thing that this distance is basically delta x, and this distance is basically delta x divided by 2. Okay, so that I've said earlier. So if I go to the treatment of the boundary nodes, these boundary cell centroids, boundary cell centroids. So this is basically your 1, and this is basically 2. So what I'm dealing with is basically the left hand side of the that rod itself, rod or bar, whatever you call it to be. So this is your small w. For example, T is basically equal to 100 Kelvin or something like that. Let us consider T as of now. So TA itself will be given the temperature at the both side of the rod. So these are basically called the boundary conditions. So this is basically delta x divided by 2, and this one is basically delta x. Okay, so this is P. P is basically my cell centroid of interest, and capital E is the eastern cell centroid, which is adjacent to that of the cell centroid at the eastern part of P. Okay, so then I can write it to be like Ka dt dx at small e minus of Ka dt dx at small w plus is delta v equal to 0. Okay, so now dt dx at small e, that I can do. So this is basically small e, which is the common phrase between capital P and capital E. So therefore, I know that this will be equal to what? T minus Tp divided by delta x, delta xp or delta x itself. And this one is basically equal to that of Ka T1 minus, or you can write it to be like Tp minus Ta divided by delta x divided by delta x Pa, or which is basically equal to delta x Pe divided by 2 plus SdV. Okay, so if P itself is 1 and this is 2, then this becomes Ka delta xp. I'm considering it to be delta x, since the cell size is basically the same for all the cases of all the control volume. You can consider it to be delta x. So this is T2 minus T1 minus of Ka delta x by 2, uh, T1 minus Ta plus SdV delta V equal to 0. Okay, is it clear to all of you?
Yes, sir.
So this formula is basically called the forward difference formula. Okay, so as you can see it here, sorry, this one is called the forward difference formula. So this one is the order of accuracy of a formula difference formula. The forward difference formula is delta x, and whereas for the central difference formula, that is delta x square. Okay, so you are basically having two kind of discretization, having different order of accuracy when you are discretizing the equation at that of the boundary cell centers or boundary control volumes. Boundary control volumes. Okay, is it clear to all of you?
Sir,
Uh,
uh, Sir, once repeat I understood the first two steps, but Ka T2 minus T1 by delta x, that I didn't understand, sir.
This Ka, huh, because T2 minus T1 I'm writing because I can number it, okay? So what I initially did was actually I divided the domain into six control volume. One, two, three, four, five, six. Okay. So since I am at the leftmost part, so P corresponds to number one and E corresponds to number two. So instead of E I am putting number two and instead of P I am putting number one. So similarly in the next expression itself, so TP is T1 and TA is TA. So from the letter itself you can change it to the number.
Okay, sir. Sir, A stands here the leftmost boundary, sir.
Yeah, the leftmost boundary.
Okay, sir.
Okay. So this will be handy. This kind of formulation you have to do before you do your code in MATLAB. And I'm showing you that for the boundary cells how to do it. Okay. So initially I showed you for the interior cells how to write the equation. So for example, if I ignore the source term here, let us ignore it. So what I'm doing is basically I'm further simplifying it by taking off the source term. So there is no source term. So now this becomes Ka T2 minus T1 divided by delta x minus k T1 minus Ta divided by delta x divided by 2. So the third term I am not considering since I am considering that there is no source inside that inside our control volume. So this actually becomes, if I simplify, 3k by delta x T1 equal to 2k by delta x Ta plus of k by delta x T2. Okay, is it clear to all of you?
Yes, sir. Sir, one doubt, sir.
Okay, please.
Yeah, the last step that you took T2 minus T1, right? And you said that it's an order of accuracy of second order.
Okay,
So
yeah.
can you please repeat why is it in second order and the other forward difference is in first order?
That I have to go to the finite difference class itself. In the previous class, I have derived. So this is by using Taylor series expansion you can derive. Uh, Now I've also shown you.
Okay.
I think,
Yes, sir. I know that one, but I didn't get it. So
so this is basically
so
your
you have
bot.
used the central difference, right? For
Yeah,
that.
yeah. Central difference is
Okay,
a
okay, okay. Then
then forward difference is basically your boundary cell centroid, and for the
yes, yes.
cell centroid which is adjacent to one, which is basically your second cell centroid. For that, I actually use the central difference. Okay.
Okay, okay. Then it's fine, sir. Actually,
Yeah.
okay, fine. Central
So
difference is second order, right?
this is basically 2 delta x it is written because the distance between phi j plus 1 and phi j minus 1 itself is 2 delta x. Okay. But in our case
Okay, okay.
itself,
Then
the distance
it's
between
half
P
half
and
the
E
length. Okay,
itself is basically delta x. Okay. That's why
okay,
what you have to do is
okay,
phi P minus phi E divided by delta x. And that's why
okay,
in the
okay,
forward difference also in the denominator you are getting this delta x divided by 2. So that thing you have to take into account. Okay.
okay, okay. Thank you, sir.
Uh, so so as you have seen, there are two order of accuracy. So we will also discuss about what is the order of accuracy of the overall the numerical scheme that I'm using here. So if there are some first order and the second order of accuracy, so that I will discuss. So then what I'm doing is basically I have to go to the other side of the boundary also. So now this one is basically the your P, which is basically if I consider five cells within the domain, let us consider it to be five, this one, there are five cells in the domain, and this one is B. So now I will deal with the fourth and the fifth control volume. Okay. So I have to go here. This one is a fourth control volume and this one is a fifth control volume. So this is capital W and this is capital P. Okay. So similarly now this becomes K delta X delta T delta X minus of Ka dou T dou xw equal to 0. So now delta T delta x at east is basically equal to what? Tb minus T5. So if this one is Tb and T corresponds to 5 and W corresponds to 4, so Tb minus, sorry, this is Tb, Tb minus T5 divided by delta x divided by T. Okay, so delta T delta x W equal to Tp minus Tw divided by delta x, which is basically T5 minus T4 divided by delta x. So now this becomes Ka Tb minus T5 divided by delta x divided by 2 minus of Ka T5 minus T4 divided by delta x equal to 0. Okay, so this one is basically called the backward difference formula. Backward, since I'm considering it at the east face itself, so Tb corresponds to that of the east face. So what I'm doing is basically I'm taking a point on the left hand side of the that face itself, and that's why it is called the backward difference itself. So if you go to the derivation in the finite difference class itself, and also to the derivation that I've done previously in this class, so you will see why I'm saying this. So this actually becomes Ka, uh, this one, T5 3Ka by delta x. So I'm considering the K and A to be same over the whole domain. Delta x T4 plus 2Ka by delta x Tb. Okay, is it clear to all of you?
It's
Please. So do you have any doubt until now? तो अभी तक हो चुका है, ठीक है, तो दोनों साइड में मुझे मिल गया कंट्रोल वॉल्यूम का इक्वेशन, ठीक है, T5 और T1 के लिए, और बीच में जो 235 था 234 था उसका भी मिल गया, ठीक है। तो इसके बाद हमको क्या करना पड़ेगा, वो जो इक्वेशन का सेट है वो मुझे बनाना पड़ेगा। ओके, सो नाउ 3K,
sir.
हाँ प्लीज।
Sir, can't we cancel all the K terms? I mean,
Yes, yes, you can do it. We can do
okay,
it.
sir.
But I'm writing it for the point of view. For example, if you are using a source term, you will just add on the right hand side of the equation. Okay. You can cancel
Okay, sir.
the terms itself. A by delta x from the both side of the x equal to b matrix itself. That can be done.
Okay, sir.
This will basically, for example, if I considered it to be the rod itself, and this one is TA and this one is TV. For example, this is 500 Kelvin and this one is 100 Kelvin. Okay, so you will basically get a linear temperature like this. Okay, which is something like TV plus TA minus TV divided by L multiplied by X. So X is basically coordinate from here. So since you are cancelling the K terms from the both side of the equation, it actually becomes independent of the property itself. So Tx is basically Tv plus of Ta minus Tv by L multiplied by delta X. Okay. So this is an analytical solution by the way. Okay. So then this for the first cell centroid, we basically need to be got it to be like 3K by delta X multiplied by T1, and this is equal to 2K by delta X multiplied by Ta plus K by delta X multiplied by T2, and the second term is basically 2K by delta X T2, K by delta X T1 plus of K by delta X T3, 2K by delta X T3 equal to K by delta X T2 plus of K by delta X T4. So these are for the this is for the second cell centroid, this is for the third cell centroid, and this one is for the fourth cell centroid. P4 equal to k by delta x P3 plus of k by delta x P5. Similarly, this is for the fourth cell centroid. For the fifth one, which is basically on the right hand side of your heat conducting rod, whatever you call it to be, if it's a heat conduction equation, since we are solving for uh, the temperature itself, that can be treated as a conduction problem without a source term. So this actually becomes 3k by delta x multiplied by T5 equal to k by delta x multiplied by T4 plus k by delta x divided multiplied by Tb. So this is for the fifth cell center. Okay. So are the four equations clear to all of you? So these are for the five. These five equations are for the five control volumes in our domain. Since I have divided the whole domain into five control volumes. So is it clear to all of you?
Yes, sir.
Yes, sir.
So
So
in the last equation, I think it is 2k. Uh, um, 2 is there in the
no no.
last equation.
In the last
TB1.
it's हाँ टीवी वाला जो है वो तो थ्री होगा ना. This is 3k by delta x multiplied by
2 TB.
think
2
हाँ
TB.
yeah. This is 2 TB, sorry. Okay. So then what I have to do is basically convert this into a matrix format, which is basically Ax equal to B format. So now this becomes Ka by delta x, and this actually becomes 3 minus 1 0 0 0 minus 1 2 0 0 0 0 minus 1 2 0 0 0 0 1 2 0 0 0 0. So this means minus 1 3 T1 T2 T3 T4 T5. So this is basically equal to 2 Ta 0 0 0 2 TB multiplied with Ka by delta. So is it clear to all of you?
Yes, sir.
So that's how it works. So then this actually comes here to be Ax equal to B format. So X is basically what? A inverse B. Okay. A inverse B. So let's take a give me 5 minutes. Okay. So you think that do you have any doubt or not? I will join you shortly. Okay. So for 5-10 minutes, think that do you have any problem or regarding the equation itself or that what I have taught in this class? So I will be back. Okay.
Hello, anyone?
Sir,
Yeah, Vasundhara, this is Pawan actually.
sir, I didn't get you, sir.
This is Pawan. I'm also a student like you.
Okay, okay.
Uh, so I had a doubt. How many classes has been done till now?
This is fifth week.
Yeah, fifth week I know, but this Zoom classes, right? This online session.
I have been, I mean, this is my second class.
Okay,
And for previous classes, I could not able to attend.
okay. Yeah. That's the same issue with me only. So that's why I wanted to clarify what has been covered.
I too don't know.
Okay. So registered for the exam.
Hello?
Yeah, have you registered for the exam?
Yes, yes, I have registered for the exam.
You're doing BTech, huh?
No, actually, I'm planning for my PhD, so that's why I'm learning. I'm a faculty,
Oh,
actually.
oh, sorry, sorry.
Okay. Sir, sir.
I think he's not available.
Yes, yes. I mean, hmm.
May I know what what background are you from?
I'm from machine design.
Okay.
So that's the reason. Actually, I don't know nothing. I mean, I have no idea about CFT. And this is the first time
Okay.
I register for this exam.
So
What about you?
yeah, mine's big story. I I'm doing MTech in Madras and also working right now.
You're doing your MTech.
Yes.
You are from thermal specialization.
No, not exactly thermal specialization. It's computational mechanics actually. So
So am
related
I
to this
audible?
this
Do you have
field.
any doubt?
No, sir.
Uh,
No. Still no, not.
Sir,
Yep.
I mean, should we use any iterative methods to solve this problem, sir?
Yeah, if the matrix is small, you can directly invert it by using uh, Cramer's rule or something like that. But if the matrix itself is large, then you have to use iterative methods like Gauss-Seidel method or Gauss elimination method that you have to do.
Okay, sir. Okay, sir.
You have to use iterative method for that. Otherwise, taking the inverse of a matrix actually becomes memory intensive. So it consumes a
Uh,
large amount of RAM. That should not be the case itself.
okay, sir.
Sir,
So
I have a doubt.
yeah, yeah, please.
Sir, it's the regarding the Navier-Stokes equation only, the
Yeah,
starting equation that you wrote.
yeah.
So I have a statement. Just say it whether I am true or not.
Okay.
So if we consider phi as a vector field,
Hmm.
so there is a nonlinear term, right? Rho into V into V.
Yeah, yeah, yeah.
One V will be related to the field itself, and another V will be related to the fluid particle, right?
No,
Is
no,
it
both
that
of
way or else?
no, no. For both of them are basically related to the fluid velocity itself. And the
Okay.
concept of particle actually comes into play when you consider that to be an Euler-Lagrange one. That treatment is different one, but
Yeah, yeah.
both the velocity
Okay.
are actually the velocity field in the domain itself. Okay.
Okay. So if you consider that phi is as a scalar quantity like your temperature you said, so its scalar is getting also transported with the respect to the velocity field only, right?
Yeah, yeah. All the
So
scalars actually
how
get.
can we now how can we say that we are following a Lagrangian approach or an Eulerian approach in this using the temperature?
No, no. That is not typically what we call it to be a Lagrangian approach. That is a bit different.
Okay.
So what happens is that what is the difference between a Lagrangian approach and an Eulerian approach? So first get to that point.
Uh,
So
okay.
Eulerian approach is basically you have a domain like this, a box like this. Okay. So for
Okay.
example, a small box is given to you. Okay. So
Yes.
Then this box is given to you. Then I said that please find out the density. So your main instinct will be what? Del V. So this is basically del M by del V. This is your density. Okay. So for example, there are some 25 particles in the domain. 25 particles. And at a time instant itself, for one time instant, this is 25 particles. Okay. So 25
Okay.
multiplied by mass of each particle, and which is basically
By
divided
entire
by
one.
your delta V. Okay. So in the next time instant, what happens that five particles actually come inside the domain because the particles are in random motion with each other. If I if I'm finding out the density of a gas, so the particles are in random motion with each other. So the five actually come into play. So instead of five, that will be 30. So there is a substantial error in the estimation of your density. So what you do is basically you increase the control volume. So after some time, this oscillates and this becomes a constant. Okay, so if I increase the control volume delta V itself, for example, in delta V there are 10 to the power 23 gas molecules. So if five molecules actually comes into the domain or five molecules actually comes out of the domain, it doesn't matter. Okay, your density actually remains
Okay.
constant. So what happens at your density or some field, for example, your velocity or temperature, that becomes a continuous function of what? Your space and time. Okay, x, y, z, and t. Lagrangian approach is a different one. Lagrangian approach, what you are doing is basically you are tracking each and every individual particles. Okay.
Yeah.
Here you can't
Okay.
track 10 to the power 23 gas molecule. It is not possible. Okay.
Okay.
If you are going to track, then you have to solve this Newton's law of motion like m square d squared x dt squared equals to net force which is acting on the gas molecules. It is not a possibility. Okay. So where do we use this Euler-Lagrange approach? For example, there is a particle latent flow itself. Okay. For example, there is a particle latent flow. Particle and gas both are flowing into the medium. So the upper plate is basically your wall. So typical canonical channel flow. I don't know whether you have come across this or not. So this one is wall. The plate which is below that is also a wall. Okay.
Yes. Yes. Yes.
Okay. So then what happens is that your gas plus solid is entering into the domain. So one approach is basically you consider both to be an Eulerian phase. Okay. Which is called the Euler-Euler multiphase approach. Euler-Euler multiphase approach. Okay. And then so what you are going to do is basically you solve this solid by using KTGF model, kinetic theory of granular flow. There is a model, something like that. You don't have to know as of now. So what it does is basically you consider the solid to be a continuum medium like the gas itself. Okay. Otherwise, what you can do is basically you can track individual solids. So for example, there are some solids which are inside the domain, which I'm marking by using this blue color. So you can track it. Okay. The gas is flowing in which the solids are basically dispersed. Then you have to solve this m squared dt squared equals to f net. Okay. So this can be done when the solid particles are basically less in number. Okay. So it is of the order of 10 to the power 23. It is not a possibility. If it's in the order of 10 to the power 6, maximum case it is in the order of 10 to the power 8. That can be done by using high performance supercomputing. That can be done. So for example, there are some 1000 particles in the domain 10 to the power 3. You have to solve 10 to the power 3 equation for that of the solid phase itself. Whereas for the gas phase, you have to solve the Navier-Stokes equation plus a continuity equation. Okay. And then you have to model the interface momentum exchange between the two phases. Momentum exchange between the two phases. Okay. So which is done by using drag, lift, and turbulent dispersion. So these things you don't have to know as of now. So this thing you have to model by using an equation. That can be done by different closure models. So what I'm trying to make you understand that if it's a Lagrangian approach, you have to track individual particles in the domain. Okay, like molecular dynamics simulation. But if it's a Euler-Euler approach, then what happens is this solid phase actually are treated like a fluid itself. Okay, so then you don't have to track it. I hope I'm clear.
sir.
Okay, so I didn't confuse you, right?
No, sir. I'm more clarity I got.
Uh, So, do you have any other problem? You can ask me.
Sir, can you please just run through a sample code for solving, like for Thomas algorithm or some other iterative method? Or, like for this
Uh,
one, it's tri-diagonal system, right? So
TDML. Yeah,
just
that can be done. As of now, as you requested, I will do it in the next class. As of now, I'm not doing it. So yes, we can do it in the next class. Yes, that can be done. Any other confusion you have? Otherwise, I will go ahead with the thing like this. Okay. So I think I should go ahead with the thing I was doing. Thomas algorithm, those thing I will do. So I may share the code with you. So what I was planning was that this 1D heat conduction problem or the convection diffusion problem that can be solved in the class itself, or I can give you assignments. But regarding the Thomas algorithm itself, let me see whether I can formulate a problem, a simple problem for you that can be done in the class itself. Otherwise, I will share the code with you along with the PDF where the problem will be written and the solution will be given. So I think that also works. Okay. So now what I'm going to show you is basically a convection diffusion problem. So now instead of so initially you saw that there was only diffusion in the domain. Okay. So another thing is basically Pawan, one thing one wanted to say is that uh, as you said earlier was that the velocity actually carries your temperature concentration itself. So this has nothing to do with the Euler-Lagrange or the Euler-Euler approach itself. That is very much what should I say? That's a normal event. So your vectors actually carry your scalars. Okay. So there are other things also that I will cover in the other classes that you will come to know with time. So if I consider a convection diffusion problem, okay, I think it is. I think it is recording. If it's a convection diffusion problem, so now this is basically your del dot rho v phi plus of del dot gamma grad phi equal to 0. So there are two terms. One is basically your convective term, another one is basically your diffusive term. As of now, you don't have to think about the nonlinearity itself. Since the velocity itself, I will give it to be a constant one, and phi is basically your temperature field that you have to solve. Okay, and I will apply the Gauss divergence theorem. So which actually makes it to be a linear one. And then this one is basically ddx of rho u phi plus of ddx of gamma d phi dx equal to 0. If it's a 1D problem, for example, this is a x-axis and the convection and the diffusion is only happening in the direction of the x-axis itself, and this one is y, this one is uh, z, and this one is x. So x starts from 0 and it goes to L. Okay, so x equal to
sir,
0 to L.
sir, one doubt, sir.
Oh, please.
So in the governing equation, the convective terms and the diffusion terms are on the either side of the equality sign, right? So there should be a minus, right, in between.
That will
Means,
matter. Yeah, that doesn't matter. So this dt, yeah, I'm done. So minus of this will be there. So if I actually take it to be like del dot rho u phi dv control volume p minus of control volume p del dot, now it is right. So kind of phi d. Okay. So is it clear to all of you? So what I've done is basically I've taken it to be a volume integral and then I've integrated over the whole control volume. Is it clear to all of you?
yes, sir.
Okay. So this I can convert into a surface integral. So in cap dot rho v. So v is basically your vector, which I can consider it to be a constant itself, that I will discuss when I will tell you the problem which you have to solve. So this one is basically your waist. So eta cap dot rho v phi dA equal to, this one is basically, I can write it to be like this. I think this will be much more easier. This one control volume P or your area A is basically equal to area A eta cap or in cap, this one, okay, multiplied by d. So I've considered both of the volume integral into a surface integral. So is it clear to all of you?
Yes, sir.
So no doubt now this can be converted into in cap dot rho v phi dA plus west in cap dot rho v phi dA in e in cap dot rho at phi dA plus west of, sorry, in cap dot gamma grad phi dA. Okay, grad phi dA. Okay. So now your in cap will be equal to that of, this is your I cap, this is your minus I cap, this is your I cap, this is your minus I cap. So this will be equal to that of rho UA multiplied by phi E, since B vector is basically equal to what? U I cap plus 0 j cap plus 0 k cap. Okay. So now if I make a dot product between I cap and I cap, that actually becomes 1. So this will be equal to rho UA phi E, rho UA phi W equal to gamma A d phi dx E minus gamma A d phi dx W. Is it clear to all of you? Hello,
Yes,
am I
yes,
audible?
yes, yes.
Sure. So what you have to do is basically, then you have to discretize the whole thing. So for that you have to do is basically uh, this rho, I have to write the control volume once again. So this one your P control volume, this is your E control volume and this is your W control volume, and this one is small w and this one is small e. So then phi E is basically equal to phi P plus phi E divided by 2, and phi W is basically equal to phi P plus phi W divided by 2. So these are also central difference formula. Okay, so these I will derive as of now. Central difference. an issue. Hmm. Give me a time to sort this out, otherwise this will pop up when I upload the recording. Mhm. So this is basically the central difference formula, and I have to derive it. So uh, this central difference formula, how to derive it? So as I have shown you earlier, that phi j plus 1 is basically your phi j plus d phi dx delta x plus d square phi dx square delta x square divided by 2 factorial and so on. Similarly, phi j plus minus 1 is basically phi j. Uh, then this is equal to that of minus of d phi dx. Sorry, phi j is basically, or phi I or phi j, whatever you call it to be. So j is for the y and I is for the x. So it can be I, it can be j. So as of now, I'm using the j subscript. So this is equal to phi j minus 1 is equal to phi j minus of d phi d. It should be I. Otherwise, I can't get with it. Delta x plus of d square phi dx square delta x square phi. Okay. And now what I have to do is to multiply this by a, multiply this by b, and multiply it by c. So this actually becomes a I j minus 1 phi, sorry, j I minus 1 phi I minus 1 plus c phi I plus 1 equal to a plus c phi I plus c minus a d phi dx delta x plus of c plus a d square phi, sorry, d square phi delta x square delta x square by 2 factorial plus c minus a d cube phi dx cube delta x cube. These I have derived in the previous class, by the way. So I'm directly writing it. I hope I am right. So a plus c is basically equal to 1. So in the previous class, I have taken it to be c minus a equal to 1 and a plus c equal to 0, since I only wanted to find out the derivative. But now I am basically finding this phi j as a function of phi j plus 1 and phi I as a function of phi I plus 1 and phi I minus 1, and therefore a plus c is equal to 1. I think Vasundhara actually asked me in the previous class. So now a is basically half, c is basically half. So now this becomes uh, I think this is not required. B's will not serve any purpose, by the way. So then this becomes phi j minus 1 divided I minus 1 divided by 2 plus phi I plus 1 divided by 2 equals to phi I plus c plus a d square phi dx square delta x square by 2 factorial plus higher order term. Okay. So phi I am expressing as a function of phi I minus 1 and phi I plus 1. So is it clear to all of you how this I am calling it to be a central difference? This is of the order of delta x square, by the way. Okay. So is it clear to all of you? This one is a leading order error. Leading error. And this is basically all the terms is basically your truncation. Is it clear to all of you?
Yes, sir.
Yes, sir.
And then what I have to do is basically I have to use that in the convection diffusion problem. So this one becomes your uh, this rho u. Uh, Let us use some nomenclature in order to make our life easier. So this one is basically I'm considering it to be Fe, and this one I'm considering it to be Fw. So this becomes Fe phi e minus Fw phi w, okay, equal to gamma a d phi dx. So gamma a can be written in the format of this gamma a by delta x, or it can be written in the format of this a can cancel out from both sides. So let us do like this. Let us do d phi dx e minus of gamma a d phi dx w. So now this can be written as gamma a by delta x. I'm writing it to be as so first I have to draw the control volume. So this is your P control volume, this is your E control volume, and this is your W control volume. Okay, तो उसके बाद मुझे this. So what will be this phi small e, and this will be phi small w. Okay. So what will be phi small e according to the central difference formula? Any of you in the class? What will be phi small e? I derived it now. So you can use this expression. So do
Phi
anyone
plus
phi?
phi capital E plus phi p by 2. Okay, 100.
And this will be another one will be phi p plus phi capital W divided by 2. Okay. Sorry, this one will be FW. Okay. So another thing we can write it to be like, if I am considering gamma a by delta x to be equal to d, so this will be equal to d e phi e minus phi t minus of dw phi p minus phi w. Okay, so is it clear to all of you?
Yes, sir.
चलो ठीक है, इसके बाद क्या करना है? So your if e, or one thing I can do is basically phi p is if e divided by 2 minus of if w divided by 2, or I can write it to be like this. This whole thing can be written in this format: AP phi p equals to AW phi w plus AE phi e, where A is basically equal to that of AW is basically equal to that of DW plus AW divided by 2. AE is basically equal to DE minus AF divided by 2. Okay, and AP is basically equal to AW plus AE plus AP minus AW. Is it clear to all of you what I've written?
Sir, Fe and Fw will be equal, right, from continuity equation?
Yeah, that is called conservativeness. Fe and Fw will be equal. This term should be 0. So when I'm actually solving the equation, I should check that whether Fe and Fw are basically equal. So there are three things when it's called conservativeness, transportiveness, and accuracy. These three things I actually said in the previous class that I'm going to discuss in this class. So this is basically what we call it to be. conservativeness. So this is basically conservation of mass. So one of the thing you can clearly see is that, for example, if I this is a convection diffusion problem, right? Diffusion, convection and diffusion problem. Convection plus diffusion problem. So for example, if I consider this Fe and Fw to be equal to 0, then this reduces to be what? Aw is basically what? Dw. E is basically what? De, and Ap is what? Aw plus E. So this equation I'm solving for that of the interior cell centroid itself. So if you go back, then you will see that this is the diffusion problem. So if I actually make the flow velocity to be 0, this actually reduces to a diffusion problem. So one thing you can easily see here is that one of the main advantages of writing this format, that AP phi p equal to AW phi W plus AE phi, is that you can write directly in the program itself, and then according to the type of equation you are solving or the discretization equation you are solving, you can write an if statement. So if it's a convection equation, I will consider this the AW and AE to be this, and AP is basically this one, this AW plus AE plus AP minus FW. So if it's a diffusion equation, if it is, then I will go with this one. So you can use an if statement, you can use a switch case in order to change the value of the AE and the AP itself, and this will automatically change the equation you are solving for that. So that's the advantage of expressing in the terms of AP, AW, and AE. Okay. So is it clear to all of you? Hello, am I audible?
Yes, sir.
Yeah,
Yes, sir.
yes,
So uh, then another thing we have to do is basically solve the boundary problems also. So that I will do as of now. So similarly, consider there were 5 cells in the domain itself. The node one, sorry, cell centroid one. Okay. So I think we can easily do it. So for the cell centroid one itself, so if it this one is P and this one is E, so this one is P and this one is E, and this one is small w and this is small e, and P corresponds to 1 and E corresponds to 2, and this one is a control volume. So the total length is delta x, and the distance between the boundary and the P cell centroid or the first cell centroid is basically delta x divided by 2. So then what you have to do is basically Fe minus phi minus Fw Aw phi W is basically equal to that of gamma E A delta x delta phi delta x E minus gamma W A W delta phi delta x W. Is it clear to all of you? So phi W we already know, that is basically equal to phi E. A. Phi E is basically the temperature at the left hand side of the that rod for which we are basically solving this convection diffusion equation. Okay. So phi E is what? Phi W we know, phi W equal to phi A, that comes from the boundary condition itself, and phi is what? Phi P plus phi E divided by 2. D phi dx at east phase is basically what? Phi E minus phi P divided by delta x. Similarly, d phi dx at small w is basically equal to that of phi P minus phi A divided by delta x divided by 2. Okay. So is it clear to all of you what I've written? So now I can write Fe multiplied by phi P plus phi E divided by 2 minus phi Fa phi A, and this is basically dE phi E minus phi P minus dA, d capital A. So, or you can write it to be like dA is basically phi p minus phi A. So, dA is basically 2 times of gamma A by delta A, whereas d small is basically gamma A by delta A. Is it clear to all of you?
Yeah.
Okay.
Yes, sir.
Similarly, for the fifth cell set, right? This is P, this is B, and this is W. So this one is yeah. So this is small w. This one is recording. Yeah, it's recording. This is small w. So this one is fourth. This one is fifth. So this is rho u phi. I can directly write. So uh, F phi e minus of F w phi w equal to gamma a d phi dx e minus of gamma a d phi dx w. So now what is this is E, right? This is sorry, this is small w and E is basically this one. That's how your cell volume looks like. So this becomes phi b minus of f w. So this actually becomes phi w plus phi p divided by 2 equal to uh, db phi p minus sorry, I should not write gamma a divided by delta x, and this is phi b minus phi p delta x divided by 2 minus of gamma a by delta x phi p minus phi w. Okay, so now this can be written as db, which is basically 2 gamma a by delta x phi b minus phi p minus d w or d whatever you d small w phi p minus phi w. Okay, is it clear to all of you? Hmm? Hello, am I audible? Is it clear to all of you?
Yes, sir. Yes,
Yes,
sir.
sir. Yes, sir.
Uh,
चलो ठीक है, तो इसके बाद क्या करना पड़ेगा, इसको थोड़ा सा ठीक से लिखते हैं। ए पी फाइव पी नहीं तो पीछे लिखते हैं ए पी फाइव पी. This may be a bit overwhelming for the first time, but once you start doing it, uh, it will be easy for you. So this one is basically equal to that of plus db phi b minus of if. So if is basically your coming to be fb, so it should be b. So this is equal to minus of fb phi b. So aw is basically equal to fw divided by 2. aw is basically fw divided by 2 plus dw, and ap is basically equal to that of db plus dw, dv plus dw minus fw divided by 2. Okay, so this one is a fifth equation. Okay, so is it clear to all of you? So now what
Yes,
I'm
sir.
going to do is basically I'm going to convert this equation for a sample problem itself. So for example, if E is basically zero point 0.1 meter per second, rho is 1 kg per meter cube, okay, 1 kg per meter cube, and gamma by delta x is basically zero point 0.1 divided by zero point 0.2, since it's actually a one length divided into 5 cross sections. So that's why it is coming to 0.2, which is basically a 0.5, and phi is basically equal to 1 and phi b equal to 0. Okay, so then for the first point itself, if you remember the equation that I've written, first equation, it is basically dE plus dA plus AP divided by 2 phi p plus equal to dE minus FE divided by 2 phi E plus of FA plus dA phi A. Okay, so if I consider the area to be a unit area, so 1 unit or 1 meter square. Yep. So then it comes to be like area also gets cancelled from both sides. So then it becomes this equation can be reduced to dE actually becomes your zero point 0.1 divided by zero point 0.2, which is basically 0.5. Then dE is basically equal to 1, 2 times of that. Fe is basically equal to zero point 0.1 and Fe is basically equal to zero point 0.1, and so then it becomes like 0.5 plus 1 plus zero point 0.1 divided by 2 phi 1 equal to zero point 0.5 minus zero point 0.1 divided by 2 phi 2 plus of zero point 0.1 plus 1 phi is this basically this one. Negative sign is found here. This is basically phi e. So this becomes 1.55 phi 1 equal to 0.45 phi 2 plus 1.1. Okay. So this you can easily find it at home. So similarly, if I go for the fifth equation itself, which is at the right hand side of the domain itself, then this reduces to dt plus dw minus 8w divided by 2 phi b fw divided by 2 plus dw phi w plus db phi b minus fb phi b. Okay, so db is basically equal to 1, dw is basically equal to 0.5, and fw equal to 0.1, so 0.5 itself. So this reduces to 1.4555 minus 0.5554 equal to 0. Phi b is basically 0 by the way. Phi e is 1. That's why you don't have a term on the right hand side of the equation. And for the second, third, and the fourth equation, second, third, and fourth, this you can find it at home. So this becomes phi 2 minus 0.55 phi 1 minus 0.45 phi 3 equal to 0. Phi 3 minus 0.55 phi 2 minus 0.45 phi 4 equal to 0, and then phi 4 minus 0.55 phi 3 minus 0.45 phi 5 equal to 0. Then what you have to do is basically convert that similarly into a matrix format, and then you have to solve it. So matrix actually comes it to be like this. 1.55, 0.45, 0, 0, 0, 0.55, 1 minus 0.45, 0, 0, so 0 minus 0.55, 1 minus 0.45, 0, and this is 0, 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 0.55, 1 minus 0.45, 0.55, this is 1.45, this is coming to be like 5.1, 5.2, 5.3, 5.4, 5.5, and this comes to be like 1.1, 0, 0, 0. So, is it clear to all of you?
Yes, sir.
Yes, sir.
So this thing you have to do, and then you put that in the equation itself, and then you solve it by any kind of iterative method. Is it clear to all of you? Do you have any questions? So as of now itself, you know that how to treat the interior cells itself, and you also know that how to treat with the boundary cells. Only the treatment of the gradient and also the value of the variable at the cell faces that will change since we go for one discretization scheme to another discretization scheme. So the whole philosophy remains the same. Only the way you discretize the equation actually depends on the discretization scheme you are using. Okay. So is it clear to all of you?
Yes, sir.
It's a,
Uh, if you have any question, you can ask me. So the analytical solution of this problem is a convection diffusion mode that actually comes out to be phi minus phi a, phi b minus phi a exponential of rho ux divided by gamma minus 1 divided by exponential of rho ul divided by gamma minus 1. So what you can do is basically if you want to look at whether your numerical problem is basically that is coming to be correct or not, you can solve it numerically and then you can for a simple case you can tally your numerical solution with analytical one. I think that's a good approach to see whether your code is working fine or not. Okay, so is it clear to all of you? Any
Yes,
questions you
sir.
can ask me by the way.
Sir, will this recording will be available for us or
Yeah, this recording will be
to
available.
forget?
This recording, the previous video I will also upload. Okay, so everything will be available, no issue.
Okay.
Everything will be made available. I think it is done as of now. So we can close our meeting and we'll meet at Monday, next Monday. And if you have any doubt, you can mail me. I will look into Vasundhara's problem and we'll get back to you. Okay? Okay.
sir, what are the topics which you are going to discuss in the next week, sir?
Next will be outpoint scheme, and I don't know whether I will be able to start with quick scheme. So there are different kind of schemes I will discuss, and then I will also discuss which I was unable to discuss in this class is accuracy, transportiveness, and conservativeness, and those things I will discuss. And after that, we will I think 2 or 3 class we will be discussing about different kind of schemes, and then I will be going to maybe giving a class which is on coding itself. Next class we can also do with the coding of this 1D problem. I think we should go with the coding of this 1D problem and the discretization scheme. I think that will be better. So I will first do the coding of the 1D problem and then I will share the code with you also. And I will also do the other discretization schemes also. And I will also do that transportiveness, conservativeness, and accuracy. These three things I will do. Okay.
Okay, sir.
Okay. So I think we should stop. So I think we will meet in the next class. Okay. Thanks.
Thanks, sir.
Thanks.
Sir,
Thank you, sir.
excuse me.
Thank
Sir.